Hello, good morning. Which of the following complex is lowest spin and which one is the highest spin? Give reason. Ferrostor 3D5 configuration, weak field region. T2G3 is E2 n equal to 5. Magnetic moment root under n plus 2 root under 5 high spin. Ferrous second D6 configuration. Strong field region T2G6 n equal to 0. Magnetic moment 0. Low spin. Application of crystal field theory. Crystal field theory is superior than valence bond theory and can explain the several observed phenomena in complex. Some of its achievements are color of transition metal complex. The major success of crystal field theory is to explain the bright color exhibited by the several coordination compounds. The major success of crystal field theory is to explain the bright color exhibited by the several coordination compounds. The color property is generally associated with d orbital configuration and possibility of dd electronic transition in a complex. Either d orbitals have been split into two sets of orbitals when a molecule absorbs a photon of visible light. One or more electron may jump from lower energy d orbital to higher energy d orbital. The difference in energy between the atom in the ground state and in excited state is equal to the energy of absorbed photon and related inversely to the wavelength lambda. Hence, the compound imparts the appropriate complementary color due to observed certain wavelength of light and the energy difference. The difference color in complex compounds arise because the different lesions generate different crystal field stabilizing energy. For weaker lesion, complex with a small crystal field stabilizing energy absorbs the light of longer wavelength and lower frequency. For stronger lesion, complex with large crystal field stabilizing energy absorb light of a shorter wavelength and of higher frequency. The complex absorbs light and reflects the remaining light. The color absorbed light is different from that of the transmitted light. Called the complementary colors is the color of complex. In fact, the following table wave number, color absorbed, complementary color, and wave number 450 blue, 400 violet, blue color is observed, complementary color yellow, violet color observed, green, blue red, blue green red, yellow green violet, green purple, yellow dark blue, orange blue, red green. For example, blue color of hydrated copper sulfate ion is due to the complementary color of yellow light. Similarly, purple color of hexaaqua titanium third ion is due to the complementary color of green light. Colorless complex. Some complex of transition metal elements are colorless. If the metal d orbitals are complementary vacant, if the metal d orbitals are completely vacant, d0 configuration like scandium third, titanium 4, or completely fulfill d10 configuration like Cu plus, Ag plus, Zn plus 2, cadmium plus 2, mercury plus 2, etc. This is because the DD transition is impossible for the electrons and do not exhibit the color. If the complex ion absorbs the light in the IR regions, lambda greater than 700 nanometer, or ion the UV region, lambda greater than 4, lambda smaller than 400 nanometer, greater than 700, and smaller than 400. The complex of the transition metal are colorless of examples. Tetras, cyanocobalt, tate, UV region colorless. How does crystal field theory explain the purple color of hexagon, titanium third, and zinc third hand has colorless? The color properties of complex can be detected with the help of visible absorption spectrum and DD transition. In hexaaqua titanium third ion, titanium atom is in the titanium third, that is the 3D configuration. When the complex ion absorbs the light in visible region of the suitable wavelength, the single electron in T2Z orbital gets excited into the higher energy EZ orbital. The single electronic transition from lower energy level to higher energy level is called DD transition or Lesion field transition. Titanium third ion, ground state with degenerate d orbital. T2G EZ in excited state. Crystal field due to Lesion field DD transition. The complex ion absorbs the green color from the visible and the complementary color transmitted by the complex ion is purple. The spectral data shows that maximum absorption takes place the colorless compounds formed by Zn plus 2 ion can be explained on the basis of fulfilled d orbitals, due to which the DD electronic transition do not take place and hence no light absorbed or transmitted are colorless. Magnetic properties of complex. The most important consequence of the crystal field theory is to explain the magnetic property and magnetic momentum of complex. The magnetic properties of the coordination compounds arise from the spin and orbital angular momentum of electrons in partially filled d orbitals. Since the magnetism is created by the spin of the electrons and hence their property depends on the nature of electrons. The transition metal complex containing the central atom or ion with one or more unpaired electrons are paramagnetic, while those with no unpaired electrons behave as diamagnetic substance. The measure of magnetism in complex is in the term of magnetic moment and by spin-spin formula. Magnetic moment equal to root under n plus 2 number of unpaired electrons. The number of unpaired electrons in any complex depends upon the following two cases. Strong magnetic field, value of delta is greater than P. The strong magnetic field lesions cause the greater splitting of the crystal field and hence favorably terms of the lowest spin complex that the number of unpaired electrons in the complex is the cis same side or zero. So the complex formed are preferentially diamagnetic or paramagnetic in nature. For example, EDTA n equal to 4, more paramagnetic. N equal to 1, less paramagnetic, 0 diamagnetic, 0 diamagnetic. EDTA contributes a charge -2 when coordinated as the lesion. So ferrous -6, ferrous +4. Weak field lesion. The weak field lesion causes the smaller crystal field splitting the complex that the number of unpaired electrons in the complex slides, so the complex formed are preferentially paramagnetic in nature. For complex ferrous tetrachloride n equal to 5, highly paramagnetic. Hexaaqua manganese, highly paramagnetic. How crystal field applied to explain color and magnetic property of metal? According to crystal field, cobalt would have D6 configuration. Ammonia lesion is strong field lesion, so that the greater field splitting. The number of unpaired electrons is 0. So H diamagnetic. Cobalt ion disease configuration weak field. N equal to 4 to paramagnetic. According to valence bond theory, strong field lesions cause pairing of electrons in 3D orbitals. So cobalt will hybridize its inner orbitals due to sp3 hybridization. All electrons get paired before the forming the bonds, low spin complex and diamagnetic unpaired electrons. How would you explain the diamagnetic behavior of and paramagnetic behavior with the help of crystal field theory? The 8 configuration, cyanide is strong field. When chloride is weak field.